Hello, everyone. We are back again for set 4. I am just posting this Thursday morning. I apologize. This is late. I've never recorded videos like this, and so there was a lot of trial and error that I didn't expect. A lot of videos got deleted. So going forward, videos will be posted Monday and Wednesday. Sets as well. Solutions will be posted. All of them will be posted at latest Wednesday. This is for set 4. Let's get into it. All right, so set 4, we are getting into kinematic equations. So velocity, acceleration, position, all in one dimension. So we say X instead of X and Y. So let's take a look at the graph that professor has given us here. I will draw a quick little rendition of it. My tablet will allow me to. All right, and we've got 2, 4, 6, 8, 10, 12. And then we've got 20, 40. We go to 100. Well, that's not gonna work. Let's erase that. 60, 80, 100. There we go. Okay, we'll do that. Let's do sharp then. Okay. All right, drawn, not beautiful, but it is what it is. Okay, so what we've been asked to do is to draw a graph of X versus T from the velocity versus T graph and find how far the particle traveled. So let's find out how far the particle traveled because our graph is very qualitative. So we're going to go like this and like this. So let's use the equation that I used in my answer solution. There are, again, a number of ways that we can do this. But let's use one of the kinematic equations so we get used to using these equations. So we've got the change in X, so delta X, which is the change in X, equals 1/2 times V, let's say F, so our final F, plus V naught times T. So really what we're doing is we're finding an average. We're taking one point, then we're taking another point, we're dividing it by 2. That's going to give us the average velocity. And then in order to find X, or the change in X, we're going to multiply our velocity by time. So if we're moving at 20 miles per second, if we move for 2 seconds, that's 40 meters. How far we traveled. So let's break this into sections. I think that's the easiest way to do it. And it's certainly the easiest way to look at a solution. So let's call this B and let's call this C. So using this equation for A, we get delta X equals, so if we start at 0, we're going to say that our V naught is 40. And if we stop at 4 seconds here, we're going to say our VF is 40 because our line is consistent. Our velocity is not changing. So if we were to take this graph and make an acceleration graph, we would have an acceleration of 0 where the velocity graph is flat. Velocity isn't changing. Acceleration is 0. Okay, so we've got VF plus V naught divided by 2 because we're trying to find the average. And then we're going to multiply that by our time. And if we look at A, our time is 0 to 4. So it's 4 seconds. So doing some quick math here, we get 160 meters. So from 0 to 4 seconds, our particle has moved 160 meters. All right, let's take B. Delta X, again, we're going to take a final velocity and we're going to take an initial velocity. And because we want between 4 and 8 seconds, we're going to take our initial velocity as 40. So V naught is 40. And our final velocity is at 8 seconds, and that's 100. So 100 plus 40 divided by 2 times, again, we've broken this into 4-second intervals. And if we do that math, we get 280 meters. Now C, again, we're going to say delta X equals, now our final velocity is 0. And our initial is 100. We've already used that one above. Notice that our final velocity is our initial velocity on our graph here. We're going to divide that by 2 to find the average, and then we're going to multiply that by our time, again, 4-second intervals, sorry. And if we do the math here, we get 200 meters. Yes, okay. So what we're going to do to find how far in total the particles traveled in 12 seconds, we're going to add all of these together. So add 160 plus 280 plus 200 together, and you get 640. Now let's take a look at a qualitative graph from the velocity to making an X over T, so a position graph. So let's just draw a graph right next to our velocity. So when velocity is constant, we're going to have a linear relationship of X and T. So when velocity is here, it's 40 meters per second. If it's a constant 40 meters per second, our position is going to change at a constant rate. So you're going to see something that looks like this. So let's do 4, 6, 8, 12. So constant velocity, linear relationship between X and T. And here, this is our X and this is our T, and this is in 1 dimension. So X is just position. So if we have a particle on a line, where is the particle on the line? So then our velocity changes, and our velocity changes at a constant rate. So we are going to have our position is going to look, it's kind of hard to draw, so forgive me if I have to erase a couple times. We're going to have, our relationship is going to be parabolic. So you're going to have either this or this, depending on if it's increasing or decreasing. So what we're going to have for B is going to be something like this. Now that is ugly, but that is as good as I can get it, I think. So then that is where our velocity is increasing. Then our velocity suddenly decreases. And so then we're going to have, so we're going to go from a this to a this. So something like that. So that is qualitatively what our graph is going to look like. So long as you have one pointing up, one pointing down in the right, you would have the right answer. All right, so let's move on to our problems from the book. So let's see here. Where is, sorry, I have the book pulled up here underneath a tab and I have too many tabs open, I think. Transit, I'm just gonna open it again. Take me too long to try to find it. It's easier just to open it again. All right, so problem number 6, parts A and B from chapter 2. All right, so we have another graph. Our graph is going to look something like this. So there are solutions online. So I'm not going to go into great depth into solving this problem because honestly, my last video went like 45 minutes and I'm supposed to keep them at 20. So sorry. This one I will make shorter, I promise. So if we just look at this graph, let's try to figure out like conceptually like what's happening and how we can look at a graph and quickly see. So this is an X versus T. So we have a particle, I think they say. Yeah, we have a particle. And it is moving on the x-axis. So it's like this little thing and it's going like this back and forth. So if we have a particle and we say that the particle, what is it? Let's do this. Okay, so we have a particle. Let's start him at the origin. Actually, let's make him a different color. Let's make him purple. Okay, he's a purple particle. All right, so our graph says that in 2 seconds, our particle moved from 0 to 10. So like this, pretend like I had a 10 here already. All right, so then in the next 2 seconds, yes, we go from 10 to 5. So we're right here at 2 seconds. Then we go back to here. So at 4 seconds, we're right here. How about I make him progressively bigger as we go along so we know where we're at? So it's like this. Okay. So then at 4 seconds, we don't move. So 4 seconds, 5 seconds, we're just hanging out here. Then from 5 to 7, we go to -6. So we're going all the way back here. That should be an 8. We end up right here. So that's how we're in negative. So then at 8 seconds, we move forward and we end up back at the origin. So just conceptually, I just wanted to kind of help you understand what's happening when you look at these graphs. Okay, so they ask you to find out how far you've traveled and what the velocity is, and you can find the detailed solutions online. Number 24, I think again is a graph. All right, so I will just, again, just kind of conceptually, let's draw this really quickly. We have a velocity versus time graph. And we have something that looks like this, like that. That's not straight. Let's do that again. All right, like this. This is -8. Right here is origin. Okay. So you were asked to find what is the average velocity at different times, and then you're asked to find the instantaneous acceleration at different times. And it turns out what they ask you to solve the instantaneous acceleration is actually the average acceleration because of the way that this graph looks. But let's look how that is so. So if we go back to so if we look at what is being asked. Okay, so what is the average acceleration between 0 and 5? So if we look at this graph, and this is V, and this is T, and this is 5 seconds. And this is 15, so this is 10. So we look at what is the average acceleration from here to here? Well, this is velocity versus time. So we're saying that our velocity from 0 to 5 was -8. That means it's at a constant velocity. So we're constantly moving forward or backward, depending on if you're positive or negative, but we're not accelerating. So when V is constant on a graph, when you have a flat line, so when your velocity graph is y = 2, you have no acceleration. You're moving at a constant velocity. So from 0 to 5, our acceleration is 0. So then it says, what is our average acceleration from 5 to 15? So we're going to go from here to here. And we're going to find what the average acceleration is. Here there is acceleration because we can very clearly see that V is changing, and it's changing at a constant pace. So we have a linear relationship between V and T. So we're going to get an acceleration there. The detailed solutions, again, I have posted. So then it asks you from, oh, it doesn't ask you from 15 to 20. So then it says find the average acceleration between 0 and 20. So then you're going to find the average from here to here. Then you're going to find the instantaneous acceleration. So the difference between average acceleration and instantaneous acceleration, which is in the book, I'm sure you've all read. Instantaneous acceleration is if I say, right now, what's your acceleration? So using the graph, we're finding averages. That is instantaneous. So if our acceleration is consistently changing, instantaneous is going to be the same as average. If it is not consistently changing, then our instantaneous acceleration is going to be different. Here, however, our instantaneous acceleration is the same as our average acceleration for what they've asked. So from at 2 seconds, you're still going to get 0. At 10 seconds, so finding instantaneous acceleration on a graph, you're going to find what the slope of the tangent line is. And the slope of the tangent line is this. The tangent line at 10, which is at your, the tangent line at 0, velocity 0, the tangent line is the line. So we're finding the slope of the line for average acceleration. We're finding the slope of the tangent line, which just so happens to be the same thing. So you're going to find that the answer is the same. Okay, so again, detailed solutions, and I've made these solutions very, very detailed. You can find online. Moving along quickly so we don't end up with another 45. And of course, if anybody is looking at this and does not understand and needs more help, please email me. I am available just about any time to go over a specific problem or go over a concept in general. If somebody needs that, please reach out if this is not enough for you. So now we're doing 20. Let's find 20. So again, we have a graph. And this is acceleration and time. So now we need to find the particle speed at any given time. And to do that, we're going to use our acceleration graph. Again, there's always a number of ways to solve these problems. We can take this, so we could use kinematic equations using what we see from acceleration, or we can take our graph and we can turn that into a V over T graph. So let's do that. And from that, we can very quickly just see what the answers are to a lot of these questions. So here's our acceleration graph. We're going to just go right below it and we're going to do a V over T graph. So our acceleration is constant, which means our velocity is constantly changing. And our acceleration, if you're looking, this is a 2, this is a positive. These are negatives. This is negative. So our acceleration is positive, which means we're going to have a linear relationship of VT. It's going to be constant, which means it's going to look like this. So from here to here, we're going to be going up. So then we see our acceleration drops to 0, which means our velocity is going to be constant. So acceleration is how much velocity is changing. Velocity isn't changing. So you're going to see something like that. Right there. Okay. So then you see that our acceleration drops to negative, which means our velocity is, we couldn't think of the word. Instead of accelerating, we're decelerating. So then we're going to see another linear relationship because it's constant, but it's going to be like that. Did a poor job of. Okay, so you're going to see that the slope is sharper because our acceleration changed more. So our acceleration drops to -4. And this is qualitatively what the graph looks like. Again, the detailed solutions are online and I have it drawn out exact for you. So from that, we can answer the questions, and the questions are asking, at any given time, what is our velocity? And you can, so what is our velocity at t equals 10? Well, you can look here and see, okay, this is 10. You can look at the graph and see at 10, what is our velocity? And then it asks at 20. And so here's 20. We can, instead of using kinematic equations, we can just look at the graph and figure out what the answer is. All right, 27, 29, and 38. I want to quickly move on so that we can answer some questions where you are going to need to use the kinematic equations and you don't have a graph to help you. I think it's important to get to them, and I'm taking too long to get to them. I apologize. I'm just wordy. Just talk a lot. All right, so let's do 38. 38 is a bigger one and it encompasses all of what we did in the first year. All right, so the problem 38. The book keeps closing on me, I apologize. I think I'm timing out here. All right, so 30, it says a car accelerates uniformly from rest to a speed of 40 miles per hour in 12 seconds. Find the distance the car travels during this time and the constant acceleration of the car. Okay, so we have kinematic equations, which are given in the book. We have a lot of them, and they can be moved around and stated in different ways. We want to take from this problem, we want to write, what are we trying to find? What do we know? And from that, we can look at our kinematics equations and say, okay, which one is going to work the best here? So we're trying to find delta x. So for A, we're trying to find delta x because it says, how far did it go? And then for B, we're looking for acceleration. So B, A is delta x, B is acceleration. Okay, so we have lots of kinematic equations that are given in the book. Let's figure out what we know. And from that, we can figure out what equation will work best and what equation will work the quickest. So we have starts from rest. So our vehicle particle, what is the car? Our vehicle accelerates from rest, which means V naught is 0. It accelerates to 40 miles per hour. Our professor was kind enough to do the conversion for us. And so our VF is 17.9 meters per second. So what else do we know? It says in 12 seconds. So we know that our time, so we could also do a T naught and a T final. Time is usually arbitrarily started. So we can almost always say, let's start at 0. So we can just have a T and we'll say T is 12 seconds. So we want to find delta x, and we actually used this equation in a previous problem. It is going to be delta x equals VF plus V naught divided by 2 times time. So for this, we can just plug in what we have. We know that V naught is 0. VF is 17.9 divided by 2 times 12, and we can get our solution. So now B asks us for acceleration. In our kinematic equations, there are a number of ways, there are a number of kinematic equations that we can just plug these numbers into to find A. But when we're solving physics problems, it is best to use an equation where we have knowns that are exact. So when we look at the problems in the book, we are assuming that our VF is 17.9 exact, or as close to exact as we can get. When we find an answer like our delta x, we know that we're rounding that. We know that we're looking at significant digits of what we're given. We don't know what the significant digits are of our givens. So we always assume that our givens are more accurate than whatever we're rounding off to. So we want to find an equation, if possible, where we don't have to use what we've solved for. So we solved delta x. If we have to use delta x, that's great. But in all of our kinematics equations, we can find one of the equations that we don't have to use delta x. So that's what we're going to do. We're going to use this equation. And then we're going to solve for a. There's actually an easier equation to use, but we have to use the delta x, which if we don't have to, we don't want to do it. Okay, moving on. So what we're going to do is we're going to solve for a. So we're going to subtract v naught. And then we're going to divide by t. And what we get is vf minus v naught all over a. So we can just plug in what we were given, and what we get is a equals 1.49 meters per second squared. Okay, again, I've gone over time. Reach out to me if this was unclear. I know that I rushed through some problems. I am more than happy to meet with you to go over them in more depth. I'll see you next week.